That is the idea of a transformer right there before you. Okay. A transformer has a primary coil on one side and a secondary coil on the other side, as you can see. In this picture, the primary has less number of turns compared to the secondary. Therefore, this is a step-up transformer. So in a step-up transformer, the secondary has more turns. In a step-down transformer, of course, it's the other way around. Step-down transformer. So there are two types of transformers. And what do you mean by step-up transformer? The output voltage, Vs, is more than the input voltage. That's why you call it step-up. So Vs is greater than Vp, and Ns is greater than Np. That's easy to remember. And the relation between them is Vs by Vp is equal to Ns by Np. That is true for every transformer. Vs is the secondary voltage, Vp is the primary voltage, Ns is the number of turns in the secondary, Np is the number of turns in the primary. At the same time, now I'm going to give you a condition that can only be applied for an ideal transformer. An ideal transformer is where there is no power loss. So you are assuming that the power in the primary is the same as the power in the secondary. Now, what's electrical power? How do you define electrical power? It's the product of voltage and current. P is equal to V times I. There are two other formulas, but P is equal to V times I. So when you say that the power in the primary is equal to the power in the secondary, you're saying Vp times Ip is equal to Vs times Is. So for an ideal transformer, can you please reduce the sound of you eating, Joe, please? I mean, for me, coming from a different culture altogether, eating itself is a problem, even after so many years of teaching. But then added on to that a physics class, and that's making a lot of noise. Thank you. Really, it was. Okay. So for an ideal transformer, Ip times Vp is equal to Is times Vs. That means it's 100% efficient. That's what it means. IPVP is equal to ISVS. Let me also add that if ever you can find a machine that is highly efficient, that's going to be a transformer. Can somebody tell me why? You can never find a machine as efficient as a transformer simply because there are no moving parts, which means there is no friction. In every other machine, friction is a major loss, causes a major loss of energy. A transformer does not have moving parts. Now, that doesn't mean that there is no loss of energy. There will be loss of energy in several ways. I'm just going to run through them. Number one, there will be heating losses in the coils. A certain amount of energy will be lost in the form of heat in both the primary and the secondary. Number two, all the magnetic flux of the primary is not going to be linked with the secondary, correct? The core of a transformer is made of soft iron. Why? It's a ferromagnetic material. What's a ferromagnetic material? That absorbs the magnetic field and transfers it to the secondary. So we've got a ferromagnetic material, but that's fine. But you're not going to get 100% transfer of the magnetic field of the primary to the secondary. That makes sense? So there's going to be heating losses, number one. There's going to be magnetic flux losses. That's what I'm talking about. Magnetic flux losses. Number two. And there's going to be what is called hysteresis losses. I'll explain that later. Magnetic hysteresis. Okay, it's not hysteria. It's closely connected. And number four, if you watch very carefully, you see that the core, which I told you is made of iron, is not a block of iron. Watch that carefully. It's not a block of iron. It's not a huge block. It's actually made up of a number of thin iron sheets stuck together and insulated from each other. Make sense? Can you see these? That shows you that there are several thin sheets stuck together. Why? See that if you rearrange that formula, you can surely you see that you get IS by IP is equal to what? That's a dangerous formula because here is the right way, here is the other way. Did you notice that? Take care of that. Vs by Vp is Ns by Np, and here it is the other way. That's about a transformer, that's all. An inductance stores energy in the form of a magnetic field, while a capacitance stores energy in the form of an electrostatic field. We've gone over that, right? And to get the formula for energy stored, we start with power. Power is the product of current and voltage. And what is the formula for voltage across an inductance? Anybody? Half of the formula is already up on the screen. So, I times E. What is the E? What is the E? E is the EMF. It's voltage. And for an inductance, last time we saw that it is L di by dt. We wrote that formula down. What's L there? Is a constant called the self-inductance, measured in henries. So it's going to be Li di by dt because of that I there. Okay? So E is L di by dt, and then you have the I. The EMF is L di by dt multiplied by I. And how do you go from power to work? Means integrate, right? In this case, power is dW by dt, correct? So dW will be integral P dt. So that's what I'm doing here. Work is power multiplied by time, so you just got to write that down. Li di by dt times dt cancels out the dt's, and then you integrate between limits 0 to I of Li di. So you're finding the power, or you're finding the energy by the time the current grows from 0 to I. That's clear, isn't it? Okay, integrate this. That's the simplest integration possible. L is a constant, so integral I di is I squared over 2, and you have your answer. L constant and I squared over 2, and so you have 1/2 Li squared. That's the formula for energy stored in a magnetic field of an inductor. And you might notice that it's very similar to the energy stored by a capacitor, which is 1/2 CV squared. Remember that? Yeah, the comparison is perfect because that's a constant for an inductance, and for a capacitor you have C. And in place of current, here you have voltage. In fact, all formulas for energy, most of the formulas agree. What is the formula for kinetic energy? 1/2 mass times velocity squared. You know, it's easy to remember these formulas. So that is the formula. Let's do a simple problem. If L is 1 millihenry and I is 1 ampere, find the energy stored. Remember that this energy is called the potential energy, therefore the symbol would be U again, potential energy. Find the potential energy. Just use that formula, find it. It's in millihenry, so you have to change it into Henry. 1/2 Li squared. Simple case of substitution. 1/2 times 10 to the negative 3 times 1, that's 5 times 10 to the negative 4 joules. Okay. Again, let's have cell phones off the table, please. That's the current through a resistance. The potential drop is the product of I and R, which is I naught R cos omega t, which is V naught cos omega t. So what's V naught? Is the peak value of voltage, isn't it? Of EMF, peak value of EMF, and its value is given by what? I don't know. Now, do you see any phase difference between the current and the voltage? Is there a phase, P-H-A-S-E, not F-A-C-E? Is there any phase difference between the current and voltage? No. Current is a cos function, voltage is also a cos function, which means they rise and fall at the same time, as you're going to see. So if you were to draw graphs will come somewhere. I said they are in phase, and there you see it. Now, on top you have the circuit, and look at this. When the current reaches maximum, exactly at the same time, voltage reaches the maximum, and so on. They both reach zero at the same time, negative maximum at the same time, so they are in phase with each other. That's how the resistance behaves. You'll appreciate this when we look at how an inductor behaves. I hope you got this. Did you get that part? Done. Now let's go to the second one. Inductor. So you're going to connect an inductor to an alternating current generator. I may not have written the current, but you can write the current again as I is I naught cos omega t. Go on. I is I naught cos omega t. That's the current. How do you find the voltage? That's for a resistance. This is a pure inductor. It has no resistance. How do you find the voltage? We used it this morning. We just used it this morning to find the voltage across an inductor. L di by dt. Did we use it? When we calculated the power di by dt, okay. Voltage is L di by dt. So now I decided to write that I is I naught cos omega t, which you have already written. Okay, put it in there and differentiate. L times di by dt. Come on. So which is d by dt of I naught cos omega t, isn't it? D by dt of I naught cos omega t. Differentiate it. It's di by dt. What's I? I naught cos omega t. So put it there and differentiate. Yeah. And you would get this. Is that correct? Yeah, I put times omega there, right? Negative, because differential of cos is negative sign, isn't it? And omega has to be written again because it's a constant. Clear? Now, if you look at that carefully, you know what V naught is. You know what V naught is. Because okay, that's the next step. Now, before that, I decided to write the sine function as a cos function. Why? Because the current was a cos function, wasn't it? So I want this to be a cos function. Can you convert a sine into a cos? I give it out. Yes. Cos theta, take away 90. So that's how it's going to be written. Or plus 90. In this case, plus 90. Let me stop. In this case, it should be plus 90 because there's a negative. Are you with me? Cos 90 plus theta gives you negative sine theta. That's what. So I write it like that, and now you know it's V naught cos omega t plus pi by 2 or 90 degrees. So V naught is very important. V naught here is I naught XL. Okay, I'm introducing a term. This is called inductive reactance. Inductive reactance. Let me write it. Or maybe I did. No, I did not. I just said what it is. Did you get what I said? Inductive reactance. Why do we call it reactance? Because watch. That's why I said this is very important. Watch this again. V naught is I naught times what? Actually, omega times L, isn't it? So You know that my XL here is omega times the inductance. That's what I call inductive reactance. And omega, you know, is 2 pi f. Right? The f is the frequency. Is that right? Mm-hmm. So finally, XL is going to be 2 pi times the frequency times the inductance, which means this is a quantity that depends on the frequency. What is XL if frequency is 0?
0.
0. What do you mean in real life by saying that frequency is 0? That means it's a direct current. A direct current doesn't have a frequency, it doesn't change. So if you apply a direct current source across an inductor, remember that the inductive reactance will be 0. That means it does not oppose a DC. Sorry, it doesn't oppose a DC. An inductor says, come on, no opposition. But the moment you start increasing the frequency, let's say you start giving it AC now, and the frequency of AC is like 10 hertz, now you know there is an opposition, isn't it? There is a reaction. What happens if you increase the increase the frequency? It gets bigger and bigger and bigger. So now you see a strange behavior of an inductor. No opposition to DC, and as the frequency increases, the reactance keeps increasing. So it could behave like a filter circuit. Don't you see that? If you wanted to filter very high frequencies, what could you do? Just have an inductor in that pack. Because you know what? It doesn't like high frequencies. So the term reactance is exactly the same as resistance. The units are the same. The unit of XL is ohm. But why do we call it reactance? Just to show you that a resistance does not depend on frequency, while a reactance does depend on frequency. I hope you understood that. Did you get that? Same unit, but reactance depends on frequency. And this is more important than I ever can tell you. Look at the graph. Look at the graphs of current and voltage. Is there a phase difference? Yes, there is. What's the phase difference? 90 degrees. Obviously, if you're not blind, you can see it. The current was I naught cos omega t, and the voltage is omega t plus 90. All right. Which is leading? The current or the voltage? Which one is ahead? From the equation, which one is ahead? The voltage. Because voltage is omega t plus 90, isn't it? What more can I do? I can't. All right, so the voltage is always ahead. And what's this? You would see that it's true. The red one. Isn't the red one ahead? You can look at it any way you like. And some people may be looking at it and say, what? But it depends on how you look at it. Look at the math function. Okay? So voltage is always ahead of current by 90 degrees. Okay. Maybe you don't need a breather. I do. I'm tired. But I do this on Fridays knowing that there's no more class I have to teach. That's the advantage of teaching on Fridays. I really love teaching on Fridays. You understood, right? I like to say, okay, put all the energy into this class. After this, I'm not teaching today. So, not on other days. On the other days, I would have to say, no, I need to conserve energy. At night, I'm coming back with you. Okay, I meant to write again inductive reactance, and that is called inductive reactance and so on. All right, capacitance. The current is the same. I is I naught cos omega t. And in a capacitance, you know that generally current is dq by dt, isn't it? I is dq by dt. Charge over time. What's q for a capacitor? What is q? It's the charge on the plates, but what's the formula for that? Connected to capacitance. CV. That's what I'm going to do. Q is equal to product of that. So first I write I is I naught cos omega t. Then I say dq is I naught cos omega t dt. That's just mathematical. Didn't you understand that? Just brought dt to the right side. That's all. And then I bring about Q. I did not write it, but it's understood that Q is C times voltage. So that's why Hold on a second. If I is dq by dt, then you know dq is integral I dt, don't you? Let me say that again. If I is dq by dt, then dq is integral I dt.
Yes.
Correct? That is what I'm doing. dq is integral. So you integrate both sides, you will get integral dq is q. Q is integral I dt. But what's I? I naught cos omega t. Are you with me? Physics done. Now do the math. Integrate that. Take the constant out. What's the constant? I naught is constant, isn't it? That's a peak. Take it out. Integral cos omega t. Come on. Negative sign, and then you got to put an omega in the denominator, don't you? Or multiply by 1 by omega, whatever. Correct? Okay. So I get I naught by omega sine omega t. Did you say negative?
Yes.
Should be a negative. I forgot to put that. Okay, put it there.
Why is the omega at the bottom? Yeah.
Because you only take a integral of
It should be I naught.
The integral of
Yeah.
Why
I don't know. And the other one is the exact same thing, but we increased it.
And the other one, we took the differential. Go back to that. Go back to that. Go back to that. I was listening and saying, okay, wait. Go back to the last one. Didn't we take the differential?
Because you use for integrals and then become the difference.
Oh, with the voltage. Okay.
We were differentiating in the last one. What are we doing now?
Hey.
So am I right? Thank you so much. Okay. All right. We are integrating. Okay. So
then it should be.
finally, voltage is Q by C, I naught sine omega t. Now, when you are integrating, there's no negative also.
Yeah.
You were pulling me wrong into that difference, and I, for a moment, I agreed. Are you with me? It's integration, so there's no negative, and the omega comes down. All right, we're coming to the physics part now. Isn't that Q? The whole thing is Q, right? And the voltage is Q by C, right? And all you got to do is put that C down. And you have your equation. Take a look at that. So now what, isn't this whole thing V naught? Uh-huh. Do you see a difference now? You compare this with the inductance. Compare this with the inductance. For the inductance in this place you got I naught times omega times inductance in the numerator. But now you got omega times C in the denominator. Don't you see it? Okay. All right. No, we have to change it to cosine. How do you change it? This time you take negative 90
And why do we have to change it to cosine?
to compare it with the current.
Okay.
All right, let's stop. Look, the current is given as a cos function, Carlos. Therefore, we would like to have the voltage as a cos function too, so that we could
So we can compare it.
compare it. And because it's a positive, you write this as omega t, take away 90, right? Cos theta minus 90 is sine theta.
Yes.
So, point number one, very crucial. Look at the difference. The voltage is lagging behind the current. What did you see in an inductance? That the voltage was leading. Here the voltage is behind, exactly by 90 degrees. Okay, second difference. This is going to be called XC. What's XC? Capacitive reactance. In place of XL, you're going to have XC. Okay. I put it as V naught cos omega t, and then when turned right, V naught is I naught XC. It's not I naught by XC, it's I naught XC. Okay, wait. Why? Hold on. Voltage is always a product of current and resistance, isn't it? Or current and reactance. That's why we put it that way. So what's the value of XC now? 1 by 2 pi FC. XC is 1 by 2 pi FC. Okay. I'm going to explain that. But first look at the graph. Isn't the graph different? The voltage is lagging here. Another thing. What about if f is 0?
Just 0. No,
What?
it's going to be defined.
Xc is going to be infinite. So put all three of them in series like that. R, L, C, L, R, C, just order it any way you want. What is this? What is that symbol? What is that? That is an AC generator. That's the symbol for an AC generator. That's a sine curve. Do you see that inside? So whenever you see that, you know it's an AC source. What's the symbol for a DC source? Yeah, straight line. Okay. Big line, small line. Showing that one end is positive all the time, the other end is negative, but not here. Keep switching. You see that? The sine curve. So this end could be positive, negative, positive, negative. That's why it's called alternating. Okay. The currents are in phase. The currents are the same. The voltages are not, in caps. Stop. This is where you either stop drawing, listen to me, because it's a textbook diagram, you can see that, and try to understand. Crucial 3 minutes of your life. Ready? And the top diagram, the blue arrow shows you the current. It's a vector. The length shows the magnitude, the arrow shows the direction, right? Through all the three components, the current will be in phase, will be the same. Agreed? Now, what about the potential drop across the resistance? How do you find the potential drop across the resistance? Just multiply the current with the resistance. V is equal to IR. Do you see that there? So the voltage across the resistance will be I naught times R. The maximum voltage across it. That's why it's VRO. The maximum voltage across the resistance is what? I naught R. You seem to make it complicated. It's not that complicated. And are they in phase with each other? Is the current and the voltage in phase with each other through a resistance?
No.
Oh my goodness. Lost you.
Yes.
Again, I'll ask that. Is the current and the voltage in phase with each other through a resistance? Flip back and look at the formulas you got. The current was I naught cos omega t. The voltage was exactly V naught cos omega t. This is like me going to a gym. It's a workout for me. The voltage and current are in phase with each other, isn't it? That's why voltage is also represented along the positive x-axis. But the magnitude may be a little bit bigger, but they are in phase. You realize that you need 101% concentration to absorb this material? Okay. Now let's talk about an inductance. How do you find the voltage across an inductance? Multiply the current I with XL, isn't it? Instead of I times R, you multiply with I times? Okay. And, well, obviously that's hidden, but I think you can see it here. It's I naught times what? XL. And what do you know about the voltage through an inductance? It leads the current by 90 degrees. And in physics, rotation in the counterclockwise direction means leading. So that vector of which showed you current was along the positive x-axis. The current through the inductance is also along the positive x-axis. And because it leads, you rotate it in the counterclockwise by 90 degrees. So the voltage is shown along the positive y-axis, right? Got it? That's why you see it along the y-axis. Now my life is easier, I hope. When you come to a capacitor, the current leads, which means the voltage lags. So that vector is rotated in the clockwise direction by 90 degrees. And what's the magnitude? The magnitude is, of course, I naught times XC. You got it? Now, you have three vectors. How do you find the resultant of the three vectors? Obviously easy. Add them up vectorially, which means you look at the inductive VL and the VC and you see they're opposite to each other. And as shown in this diagram, which is a little bit bigger? The L is a little bit bigger. It could have been anyway, right? Do you realize that either one could have been bigger or they could have been equal? Come on now, enjoy this. So if BL is bigger than this, first you take the difference between them, which would be a tiny difference, which they have not drawn. Okay, which would have been a small difference there along which axis in this case?
Positive y.
Along the positive y. Would have been along the positive y. I'll draw it. Okay? Can you give me the value of that? Whatever comes here, I'm just going to draw on top of that. So, yes, this would be how much now? I times, oh, let me write it on the other side. I know why. I times XL minus XC. Anybody understood? Guy, did you understand? I times XL minus XC? IXL minus IXC, right? Okay. So now we have the resultant of those two, and then on top of that you have, what is this? Isn't this I times R? Now you got to find the resultant of these two. What do? Complete that. Yes, and this is going to be the resultant, isn't it? All right. Square both sides and take the square root. What will you get? You will get, okay, let me see whether I have space there. You will get I times square root of, come on, R squared plus, nobody wants to help me, XL minus XC. I'll still survive, thank you. XL minus XC whole square. Is that right? Yeah, I mean, it's not complicated. Square this, add them up, take the square root. I squared, square root of I squared is I, that's why I took it out. And this looks like I times, wow, that's not a resistance. That's not a reactance. It's a combination of a resistance and a reactance, and it's called impedance. IMPEDANCE. So when you hear the word impedance, see the word impedance, you know it's a combination of a resistance and a reactance. You know the complex number method that you used in math, if you remember it. You remember complex numbers? I don't know how you wrote it. Could be written as xi plus yj. I don't know how you wrote it.
It's a plus xi.
Okay, a plus xi because, yeah, exactly. The first part is a real part. The second part is an imaginary part. Actually, you could use the complex number method to get this formula. And that's really sweet because this is a real part. And that's an imaginary part. And resistance is real. A reactance is imaginary. I'm just trying to throw light in that. Using math, you could get it absolutely without using this phasor diagram thing. Fine. Now, remember, this is called what? Impedance. So, Z is the symbol for impedance. Wait, let me just take away what I wrote. Now, impedance is Z. I will be writing over it now because I had written before, now I wrote it, but hopefully it will not be too crappy. I naught Z, V naught is I naught Z, and Z is, that's where it's part of the show. Z is this whole thing. Z is what? Square root R squared plus, throat is dry. R squared plus XL minus XC whole square. And I also want you to find that you can find tan phi from this, or tan phi. This is tan phi. Tan phi.
The x is over the y.
Yeah, tan phi is going to be this by this, isn't it?
Yeah.
What is this? XL minus XC, right? And what is this? IR. So when you divide, you will get the i's to cancel out, and you'll get XL minus XC by R. Tan phi, you'll wake up when you do problems. XL minus XC divided by R. No, maybe. I forgot the I here. The i's will cancel out, isn't it? I times XL minus XC divided by IR. Tan phi. But cos phi is important. I'll be explaining that a little bit later. But from the triangle, can you tell me what cos phi is? What's cos phi?
Or R over XL.
Okay, it'll be easy. R over Z. R over Z, isn't it? It's called the power factor. explanation will come later on. So if you're asked to find the power factor, find cos phi. Like I said, just using the math. Explanation, I'll give it to you. So I have to throw some more stuff in to make you understand that. So cos phi is R over Z. And if you substitute the values, oh, okay, that's called the power factor. Probably I did not substitute, but if you substitute, you'll get R over square root R squared plus, the whole thing, XL minus XC, whole squared. In resonance, if Z is equal to R, then you know I is I naught, and here it is, XL is equal to XC. I just wanted you to write it before I did, so that you simply don't copy. Isn't this what you did? 2 pi FL is this. I hope nobody crossed out the 2 pi's. Sometimes that happens. You thought about it. If it's on the same side, you could have done it, but yeah. So, oh, I put it wrong. That should be corrected. What is that? What went through me? Sorry for that. It doesn't matter whether I put it as 1 by 2 pi whole square root. You know that, isn't it?
Just that that's
It's in the numerator. It should be in the denominator. It should be in the denominator. Yeah. Wow. Okay. It should be in the denominator. Okay. Now look at this resonance curve. These are called resonance curves. Let me bring you up to point. I don't know with the concentration whether you will. Come back. Does the frequency depend on the resistance? No. But something does depend on the resistance. Although the frequency at which resonance occurs does not depend on resistance, the current at resonance will depend on the resistance. Because what's the formula for current? I is equal to V by Z. What happened to Z at resonance? Z became equal to R. Are you with me? So the maximum current is still dependent on the resistance. So if you have a large resistance, this would be the resonance curve that you get. That's a poor curve. That's why some radios are cheaper, some TVs are cheaper. Because look at that. Look at you can't even distinguish where resonance happened, can you? Because the resistance of the circuit was so huge that there's a slight increase in current. As you might have noticed on the y-axis you have the current. On the x-axis you have the frequency. Come on now.
Yes.
So what happens in your radio is, you may not get all of it. As we go on, you will. Different radio stations broadcast at different frequencies. I think you know that. And so when you're tuning your radio, you're trying to just tap into one station. You don't want to hear 3 of them together. That's because that will not make sense. So you just want a current to be produced for a particular frequency, which is really high, and the current for those side frequencies close to that are really low. Are you with me?
Yeah.
So you're calling for a high, sharp curve, as shown here. So if your resistance in the circuit is small, this is the kind of resonance that you're going to get, which means at one particular frequency, omega naught here, you get highest current, and you go either lower than that or higher than that. What happens to the current is it drastically reduces. So when you're tuning your radio, what you're doing is you're actually changing the capacitance. You have inductor, resistance, and capacitance. Inductor and resistor are fixed values, but the capacitance, I'm talking about manual tuning now. Remember the manual tuning where you turn that knob? It's actually a gang condenser. It's several plates of a capacitor and then several other plates that you can either move into or out. So when you tune that thing, you're either moving the plates out or in. You do know that the capacitance depends on the area of the plates. The overlapping area. Are you with me?
Yes.
So if you move it in, you're increasing the capacitance. If you move it out, you're reducing the capacitance. And you know that the frequency depends on the capacitance, doesn't it? So you kept this a constant because practically it's difficult to change the inductance. It's easy to change the capacitance. And so for a particular capacitance, you're going to get a particular frequency. And so that radio station that is broadcasting at that particular frequency is what your radio is receiving now, because it's producing the highest current, which means the highest volume, which means you're hearing it. Now, if your radio is a cheap one, it'll have a flat circuit, flat resonance. So what will happen is you'll hear several stations together. It's called fading. And also, it's so difficult for you to tune. You would have noticed that you just touch it, and you go from one station through 5 stations. You know what I'm talking about, don't you? So if you have a 7-band radio, if you know what's bands in a radio, 7-band radio, then you can really, tune into one particular station. Otherwise, you cannot. Okay. Yes, Matt.